Let's review the variational method. It's actually very simple. It's all based on the fact that if you take the expectation value of the Hamiltonian with respect to some state, then you can't get anything lower than the ground state energy. So if you're trying to find what the ground state energy state is, what that lowest energy eigenstate is, then you can just keep on trying wave functions until you get the very lowest energy, and then you know that you've got some kind of upper bound. And if you can get it sufficiently low, then you might suspect that you're getting closer towards the actual ground state. So the method is very simple. The first is you choose the trial wave function. The second is you calculate this expectation value. And then the third is you minimize this, so you have your trial wave function depend on some parameter, and you minimize that. And that gives you an upper bound for the ground state energy. Now, as we discussed last time, knowing the ground state energy can be very useful even if you don't know that you're definitely got the actual ground state. Even if you know it's lower than a certain amount, you can tell, hey, these things bind. And the example that you're doing in your assignment is helium. Now, helium looks just like hydrogen if you've got one electron, except with a stronger charge. With two electrons, it looks like that, except you've also got an electron repulsion term. And the electron repulsion term is going to be a little bit harder to calculate because when you write it all down, Mathematica is not going to be able to do it in one big hit. So in helium, you've got two electrons, so your wave function has got the coordinates for one electron and the coordinates for another electron. So when you do your integrals, you're going to end up with integrals over the three-dimensional spatial coordinates of both electrons. And when you've got your interaction term, you'll have something that looks like the exponential of stuff divided by the distance between the two vectors. Because you know that the Coulomb repulsion between the two depends on the distance between the two electrons. Now when you try and code this up, this is going to be extremely complicated simply because this mod is going to be extremely complicated. Unless you're very clever about how you construct your axes for this. So you still haven't chosen coordinates for this. And when you actually try and put this into something like Mathematica, you have to pick your coordinates. And picking your coordinates can be done with a lot of brain. So here is a hint. There are some coordinate axes. Because you can sort of see there's a spherical symmetry here, we're going to use polar coordinates in general. So there's your hint. Make of it what you will. But the main business of today is to introduce you to perturbation theory, which is one of the most important tools, not just in quantum mechanics as a calculational method, but in fact in all kinds of physics. So perturbation theory is based on a very simple idea, that small changes in a system lead to small effects. This is of course not true in some systems, such as a chaotic system, but the whole reason chaotic systems were so interesting was precisely because it was surprising to people that small changes in a system or in initial conditions could lead to dramatic effects. In general, if you add a small effect to a system, you end up with a small effect on the behavior of that system. So what do we do in quantum mechanics if we have a small variant on a known problem? How do we use what we already know? So the problem we're usually trying to solve in quantum mechanics is trying to find out the eigenstates of the Hamiltonian. So we have some Hamiltonian, and we want to know what states are eigenstates and what their eigenvalues are. And if we know that, then we can work out everything we need to know about the dynamics. However, what if we have a small variant on a known problem? So what if this Hamiltonian can be broken into two pieces? So H0 is a problem we know, and V is some extra thing, and lambda is some very small number in some sense. So H0 might be a hydrogen atom. It might be the electron going around a hydrogen atom, and this V here might be a small effect like the spin-orbit coupling, which will give us the fine and hyperfine structure. It might be something to do with the Zeeman shift. It might be magnetic fields causing the electron to see a force. It might be relativistic corrections. Either way, they might all be very small, and so we shouldn't expect a hydrogen atom to suddenly completely change character. It might just have very slightly different frequencies for the various levels that it has. So in other words, this H0 we know everything about, so we know the eigenstates and eigenvalues of that. So if we take H0, we know that we've got some states, and I'll call those EJ0, and they have certain energies. EJ0, that's not raised to the zero, that's naught, put it in brackets. But what we really want to know is the eigenstates and eigenvalues of this problem, as discussed here. Now, of course, this Hamiltonian is a function of lambda. And therefore, the eigenstates are a function of lambda, and also the eigenvalues are a function of lambda. So let's take a Taylor expansion, a power series expansion of both the eigenstates and the eigenvalues. We've already got the Taylor series expansion here. The Hamiltonian is linear in lambda, so there are no higher order terms. But these are potentially going to have higher order terms. So let's write those down explicitly. where of course we already know what these are. These things here are things that we've already solved because we know the eigenstates and eigenvalues of H0, but we don't know what these eigenvalues are, or these eigenstates, or these eigenvalues, or these eigenstates. And if you add them all up, you'll get the total actual eigenvalue of the new problem and the total actual eigenstate of the new problem. Now, because this eigenvalue problem up here must be true for all lambda, it means that we could expand out the left-hand side of the right-hand side in terms of each order of lambda, so 0th order, 1st order, 2nd order, and so forth, and each of those terms must be equal. Now the 0th order term is precisely this. We have just this term and this term. So this eigenvalue problem that we declare that we've already solved is the 0th order. Let's have a look at the 1st order terms. So we've got two terms on each side now, because we can either have the 0th order Hamiltonian with the 1st order state, or the 1st order Hamiltonian with the 0th order state, and same on the other side. Now we can take the inner product of the left and right sides with respect to the ket Ej at naught, the unperturbed eigenstates. So if we apply that to this, we're going to get, apply it to this one, apply it to this one. And when we apply it to this one, we're going to get the expectation value of these two, because that's just a number, so it can come straight out. When we apply it to this one, the expectation value of this in itself is just going to be 1. Now what do we do about this? This H0, we know the eigenvalue problem in terms of the Ej0, so we can't just apply it to Ej1, because we don't know what Ej1 is. But we can in fact apply it backwards. If we apply it backwards, we're going to get the complex conjugate of Ej0, but since it's real, it's just going to be Ej0 again. And we don't know the action of V on Ej0, so we have to leave this as it is. And then we notice that this term and this term are absolutely identical, and therefore they cancel. And we're left with a very simple result, if I just flip them around. So we've discovered that in order to calculate the 1st order shift in the energies, all we have to do is take the expectation value of the new piece of our Hamiltonian. So this is a key result. This is the 1st order shift in our energies. Alright, now what about the states? Well, we can get the states by starting back here again, and we'll collect all the terms Ej1 on the left and all the Ej0 terms on the right. And now, just as before, we're going to pre-multiply by a bra of the unperturbed states, except we're going to choose the index that is different to the index that we're looking at in this equation. Otherwise, we'll just get 0 equals 0. When we do that again, we can apply the H0 backwards. And by definition, this is an orthonormal basis, so then we apply it through here. The first term here is going to give us an inner product between two states with different indices, so that'll be a 0. So we just got the second term. So what do we have here? Here we have the overlap between the state that we're looking for, the jth first order perturbation, and the unperturbed other states. So these terms here are the coefficients of the expansion that we're looking for. So ultimately we want something like E of J1 equals something, and that equals something is going to have to be a sum over some basis, and the obvious basis to choose is the unperturbed states. So we need some kind of CKs here, some coefficients, and that's exactly what these are. So provided we can divide by these, which we can do if the energy eigenvalues for different states are different, so they're never identical. If they're identical, that's called degenerate, and so we're doing non-degenerate perturbation theory. That's what we'll do now. We'll look at the other case later. But if we divide both sides by that, then we get this state exactly. And so you can see that we've got the first order perturbed states in terms of everything to do with the 0th order, in other words, the completely known states and eigenvalues. And so that's the result we were hoping for. So we've got the first order energies in terms of the unperturbed eigenstates, and we've got the first order eigenstates in terms of the unperturbed eigenstates.